Hi friends, welcome to my YouTube channel. This is second part of lecture number 15, and in this lecture we will study the parameter calculation of one-phase half-wave uncontrolled rectifier with RL load. Now we get these waveforms in my previous lecture. On the basis of this waveform, we will calculate the various parameters for this rectifier. First is average output voltage. We know that average value of output voltage is equals to 1 upon T integration 0 to T V naught dt, and here we get output voltage from 0 to beta, and from 0 to beta equation of output voltage is equals to that of supply voltage. That's why we get 1 upon 2 pi integration 0 to beta Vm sin omega t d omega t. On integrating this, we get V naught average is equals to Vm upon 2 pi 1 minus cos beta. Now what is average value of output current? Average value of output current is simply equals to the average value of output voltage upon resistance, and we know that average value of output voltage is this. That's why on dividing it by R we get I naught average is equals to Vm upon 2 pi R 1 minus cos beta. Now what is RMS value? RMS value is equals to under root of 1 upon 2 pi integration 0 to beta Vm sin omega t d omega t. So in this way we can calculate the RMS value of output voltage. What is RMS value of output current? RMS value of output current is equals to under root of 1 upon 2 pi integration 0 to beta equation of output current dot d omega t. But from exam point of view, these two are not important. Only this formula of V naught average and this formula of I naught average are important. But you must know the procedure to calculate V naught RMS and I naught RMS, so you can easily calculate this. Now next is, here in this circuit, load is current step. Why load is current step? Because my output voltage and current waveforms are not similar. Here we can clearly see that this is output current waveform and this is output voltage waveform, and both of them are not similar. That's why this is current step load. Next is, this is half wave uncontrolled rectifier, and output power P naught is equals to V naught average into I naught average. As I told you earlier, in case of current step load, always P naught is equals to V naught average into I naught average. Now we know that input power is equals to output power because diode is ideal, and in case of ideal diode losses are zero. That's why we get input power equals to output power. And what is input power? That is equals to supply voltage RMS value, supply current RMS value into input power factor cos phi, that is equals to output power, which is equals to V naught average into I naught average. So from this equation we can calculate the input power factor. Now what is conduction angle of diode? Here we can see that diode will conduct till we get current, okay, and we get current up to beta. That's why from 0 to beta this diode is forward bias, and that's why conduction angle of diode is equals to beta. Now what is beta? Beta is simply lying between this pi and 2 pi. So beta is between pi to 2 pi. Now what is peak inverse voltage? Here this is important to understand this. Suppose this is 3 pi by 2. Okay. Now if beta is less than 3 pi by 2, this point, it means we get current up to this point. Okay. So the voltage that appear across the reverse bias diode will be this, and here we can see that this inverse voltage peak occurs. That's why if beta is less than 3 pi by 2, then we will get maximum peak inverse voltage, that is equals to minus Vm. But if beta is greater than 3 pi by 2, in that case suppose we will get current up to this point beta. Okay, so this point beta is greater than 3 pi by 2. In this case, what is reverse voltage that appear across the diode? In that case, the reverse voltage that appear across diode will be this. Okay. So we can clearly see that in this case, or we can say that you can represent it like this. We can clearly see that the maximum peak inverse voltage is less than Vm. So we get peak inverse voltage is equals to Vm, this is plus, okay, is equals to Vm if beta is less than 3 pi by 2. Now what is circuit turn off time? Circuit turn off time means time for which the diode is reverse bias, and here we can see that diode is reverse bias for this period. What is this period? This is, suppose this is beta and this is 2 pi. Okay, that's why circuit turn off time is equals to 2 pi minus beta, and we get circuit turn off time that is equals to 2 pi minus beta by omega. Okay, so this is all about this video. I hope you like this video. Thank you. Jai Shri Ram. If you got the knowledge and concepts from this video, then please like the video and subscribe the channel. You can give your views and ask any questions related to this topic in comment box. Also share this video with your friends because sharing is caring. Don't forget to press the bell icon to get the notification of my upcoming videos. Thank you.